Good morning, students. Well, we can say afternoon
Good
also.
afternoon, sir.
Yeah. So, in the last class, we were discussing about the conduction, especially. So, in conduction, we have seen the mechanism of heat transfer. We have seen the governing law. Also, we have seen its mathematical expression. So, I'll quickly write them here. So, when it comes to mechanism in solids, it is lattice vibration and flow of free electrons. And when it comes to fluids, it is molecular diffusion and molecular collision. And governing law is Fourier's law of conduction or heat conduction, also you can say. Fourier's law of conduction. And the mathematical expression for heat transfer by conduction is equal to minus Ka dt by dx. This formula we have seen. Okay, how did we get this and all? We have seen in the previous class itself. Okay, in this, tell me what is Q. Please tell me what is Q.
Heat transfer by
What is,
amount of heat transfer.
yeah,
Did-
it is heat transfer by conduction. And what is its unit?
What?
What is it?
What?
Watts. Okay, what is its unit? And A here. Okay, I told you that area is very important. And what is that area? Which area is it?
Area perpendicular to heat transfer.
Very good. Area perpendicular to a direction of heat transfer. So if it is flowing in this direction, if Q is in this direction, then this area perpendicular to it, we have to take. Very good. Area perpendicular to the direction of heat transfer. We have seen delta T is the temperature difference. The temperature difference either we can measure in Kelvin or degrees centigrade. Also, we have seen the K will be equal to degrees centigrade since this is a difference. And delta X, what is the delta X? It is representing the thickness, which is measured in meters. Area is measured in meters square. So these are the things. Here, along with this, we shall also see a term called as delta T by delta X, or I can say dt by dx also. dt by dx. This term put together will be called as temperature gradient. The temperature gradient. How the temperature is varying along the thickness, that we call it as a temperature gradient. And what will be the unit of this temperature gradient? It is Kelvin per meter or degree centigrade per meter. Numerator measured is temperature, denominator measured is distance. So it is Kelvin or degree centigrade. Both you can have in the numerator. Per meter you have to take. Okay, both you can have because it is a difference. Since it is a difference, Kelvin will be equal to your degrees centigrade. This we have seen in the last class already. Okay, and we have also seen what is K. What is this K?
Thermal
It's a
conduction.
proportionality constant, and it is called as thermal conductivity. It is called as thermal conductivity. And what is the unit of thermal conductivity that we have seen? In the previous class, we have seen unit of the thermal conductivity. What it is?
Watt by meter Kelvin.
Watt per meter Kelvin. And this watt per meter Kelvin will also be equal to watt per meter. Please tell me, watt per meter degree centigrade. Both are going to be equal. You need not have any plus 273 conversion here. Okay. So this is the thermal conductivity here. And one more thing is, I have this negative sign. Can you observe this negative sign here? So why did I keep this negative sign? Can anybody tell me? Negative sign. Okay. See, this negative sign is taken because the temperature gradient is in the negative direction. Okay. Most of the times, temperature variation, if you take a wall like this, and if this is your delta x, and the temperature is falling in this direction, okay, this is a delta t, we call it, this is t1, this is t2, it is falling, it is reducing. Okay, if it is reducing, if you take final temperature minus initial temperature, what happens is you will get a negative value for the q. So you want to take the q in positive way. So in order to make q positive, you have introduced the negative direction there. Okay, why minus sign? Negative sign is introduced to consider the positive heat transfer even in the temperature downward trend. Even the temperature is falling or the temperature gradient is falling down, it is temperature or temperature gradient, both the things. If it is going in the downward trend, in order to make the complete q positive, you have introduced a negative sign here. What is the use of negative sign here? To make q positive. That's the point here. At any given time, you have to take q in positive way. That's the reason why it is taken as negative there. And one more thing here, you people will confuse for q dot and all those things. Okay, it doesn't matter. In some textbooks, people will give you q dot here. Q dot representing the rate. When we are speaking about the q here, it is a heat transfer rate. Okay, in the heat transfer, when we write q, whether you write this q dot or not, it doesn't matter. It's always the rate only we are speaking about. Okay, so some textbooks may have q dot here, doesn't matter. In what unit you are measuring is important. If you are measuring it in watts, it is obviously rate. It is q dot or q, doesn't matter. So how you are representing is not a matter here. Remember its units properly. You will be able to quantify it appropriately. You will be able to understand it appropriately, and you will be able to represent it properly. So don't be obsessed with the representation. It can be q or it can be q dot. Doesn't matter, right? So that's one thing I would like to tell you here. And here, one more way of representing q I would like to write. So the q is written in this way also. K into A into T1 minus T2 by L. This thickness is represented with L. So this is how the expression is taken. Q is equal to Ka into T1 minus T2 by L. See, if you observe carefully, I did not put a negative sign here. Why I did not put a negative sign? Because T1 minus T2 is a positive value. So ultimately this Q will be positive. If it is dropping here in this case, I will take the positive temperature difference. You need not put a negative sign here. If it is a negative temperature difference only, you have to put a negative sign here. That is the use of the negative sign there, right? So we'll move on to our discussion about the thermal conductivity. Okay, the thermal conductivity is a very important thing, important concept as far as conduction is considered. Okay, so first let us define what is the thermal conductivity. So thermal conductivity will be the ability of the material to transfer the heat. If this value is very high, then the ability of the material to conduct heat will be very high. If the value is very less, the ability of the material to conduct heat will be very less. So let me write it down here. Thermal conductivity is the ability of a material to conduct heat. Okay, it is the ability of material. Again, something happened. To conduct heat. So this is a definition. By definition, thermal conductivity is the ability of the material to conduct heat. Higher K value will represent higher ability to transfer heat. Lower K value will represent the lower ability to transfer heat. In order to understand this clearly, let us take a simple example here. Okay, take a hot boiling water. So here you have boiling water, and in this boiling water you have a spoon. Let me say it is a spoon made by steel. It is a steel spoon, and I will have one more spoon here. This is made by wood. I will call it as a wooden spoon. Okay, the water is at a temperature of 100 degrees centigrade, and you have placed them inside and you have left it, and you touch them with your hand. Okay, when you touch them with hand, so what happens, tell me? You have touched this steel spoon and you have touched the wooden spoon. Which one will be hot?
Steel one, sir.
Steel.
Steel. Okay, this is very hot, and the wooden spoon is not going to be very hot, and you will be in position to touch it, somehow manage with it. So why is this happening? Same water, okay, same kind of a spoon, same geometry, same area, same hand, but what changed is the material that has changed. It is the steel here, and here it is a wooden here. So why is it very hot to handle, and why is it not that hard to handle? Can you please tell me the reason now? Please tell me the reason. See, the reason is simple. The reason is the K K value of steel will be very high compared to the K value of the wood. The thermal conductivity value of the steel will be very high compared to the thermal conductivity of the wood. So that is the reason why you are not in position to touch the steel spoon, but whereas it comes to wooden spoon you will be able to touch. So the thermal conductivity is making the difference here. Okay. So let us look at one more thing here. The one more thing here is the values of the thermal conductivities of these things. I'll just show you the values of these things. See, when you use your data book, I already told that you should have a data book with you. I hope you are planning to buy it, or you must have already bought it. So please have this data book with you. Please buy a hard copy. Okay, don't rely on a soft copy, because this hard copy will be allowed to the examination. Will be allowed in examination. You have to take this to examination in order to solve the problems or write answers to the question given in the examination, whether it is mid exam or it is end exam, doesn't matter. This book is allowed. Since this is online, I'm showing you this soft copy, but whereas your exam is not online, it will be offline, so have this book with you. Anyways, let us come to our point here. So in order to understand the thermal conductivity, we will have a heading in this data book called as property values. This values you have to see here. You will have various subheadings. First one is metals. Okay, and next you will also have non-metallic solids. Okay, metals and non-metallic solids. Your steel will come in this book, in this page, and your wood will come in this page. Let us go to page number 1 first. In page number 1 you will see the thermal conductivity of the steel. The thermal conductivity of the steels will be, see, this is page number 1, and it starts here. You have various kinds of steels here, the carbon steels. If you observe the thermal conductivity value, what is the thermal conductivity value of the steel? It is around 50 watt per meter Kelvin. 50 watt per meter Kelvin. And what is the thermal conductivity of steel? You can see here it is around 50. Okay, there are various kinds of steels. Okay, various kinds of steels will be there. The value will be around 50 we can take. If it is a stainless steel, these are all kind of stainless steels, it will be around 15 watt per meter Kelvin. And you can also see, yeah, stainless steels are here even more clearly. It is around 50. Okay, either you can take 50 watt per meter Kelvin here, or 15 watt per meter Kelvin. Anything is okay here. Okay. So the value of steel will be in this range. And let us move to non-metallic solids now. What is the page number for non-metallic solids? It is page number 13. So let me move down. 10, 11, 12, 13. This is the page here. These are the non-metallic solids. Silicon carbide, tri. See, you can see wood here. Okay, various kinds of woods you can see here. So all these woods will have their thermal conductivity values here again in the watt per meter Kelvin. So what are the values of thermal conductivities of the wood? Can you see? What are in what range they are in? Please tell me. their values are around 0.1 or 0.15. Okay, so the thermal conductivity of wood is 0.15 watt per meter Kelvin. That's why the steel thermal conductivity is very high compared to the, it's 15 actually, 0.15 watt per meter Kelvin. So this is 15 watt per meter Kelvin. That's why when you touch it, you are feeling the steel is very hot and wood is not so hot. The reason is thermal conductivity. The thermal conductivity has a very important role to play when it comes to the conduction heat transfer, right? So in the given materials, what is the material having the highest thermal conductivity? K, highest. Can anyone guess what is the material having the highest thermal conductivity? Are you all there? What material might have highest thermal conductivity? See, it is a diamond that has highest thermal conductivity among all materials present in this world. It is 2100 watt per meter Kelvin. And what is the K lowest? K lowest is for freon 12 gas. And this freon 12 gas will have a thermal conductivity of 0.0083 watt per meter Kelvin. So this is the highest thermal conductivity and this is the lowest thermal conductivity, right? So among your metals and non-metals, which one will have more thermal conductivity? Please
Metals.
speak out.
Metals.
Huh? Metals will have, very good. K of metals will always be greater than K of non-metals, like we have seen just now for steel and wood example just now. You can take so many examples like that. Okay. So this is one thing, and one more thing in within metals, what happens? We have to see thermal conductivity of a pure metal is greater than or less than, you have to tell me actually, pure metal and thermal conductivity of an alloy, which one will be higher and which one will be lower, you have to tell me. Okay, before you answer this question, let me give you a question here. K of so and so material A, you don't know what is that material, but its thermal conductivity value is given as 401 meter per watt per meter Kelvin, and K of some material B is given as 237 watt per meter Kelvin, and alloy is made out of this, made of A and B, and its thermal conductivity is dash watt per meter Kelvin. You have options here. Option 1, the thermal conductivity is 401 watt per meter Kelvin, and the second one as 237 watt per meter Kelvin, and the third one as 401 plus 237 by 2 watt per meter Kelvin, and the fourth option you have is 52 watt per meter Kelvin. So among these four, what will be your answer? Please guess the right answer among this. I'll wait for your answers. Yeah. So you have to respond. When you respond only,
Sure, average, maybe.
average
B,
is
sir.
one answer. B. 237 you are saying?
Yes, sir.
Okay. Any more answers?
Sir, one not one.
401. So let me tell you that all these are wrong answers. The only right answer is this one. Okay. All these are wrong answers. The right answer is this one. Okay. So why is this the right answer? We have to see. Okay. So this is not a hypothetical question, and this is a real question. For A is nothing but copper here. It is copper, and B is in reality aluminum. Okay, and you make a alloy out of it such that has 90% copper and 10% of aluminum. Okay, 10% of aluminum is the alloy you have made. See, if you make that alloy is nothing but a bronze. I hope you know what is bronze. It is actually commercial bronze. Actually, if it is a laboratory grade bronze, you will have tin and so many things also added. But if it is generally commercially available bronze, it will have only copper and aluminum. So this commercial bronze will have a thermal conductivity of 52 watt per meter Kelvin. Okay. It is not a 101, or it is 237, or it is the average of it. Okay. So the point here is the thermal conductivity of alloy will be lesser than the least thermal conductivity of its pure metals. Let me repeat this. The thermal conductivity of any given alloy will be lesser than the least thermal conductivity of its pure metals. As we can observe here, what is the lesser thermal conductivity here among this 401 and 237? 237 is the lesser thermal conductivity. So what he is saying is lesser than the least. This is least here, and even it is lesser than the least. So what is the lesser than the least option here? Only 52 is the option. So 52 will be your right answer. I hope it is clear. Is that clear so far?
Yes, sir.
The explanation is clear. Yeah. So why it is lesser than the least, we have to see. Okay. Why does it happen? Okay. Why is it so? Why it is always lesser than the least thermal conductivity of its pure metals? Okay. It is lesser than the least of its pure metals because of the change in its lattice structure. Okay. See, if you have a pure metal, the lattice structure is so robust. The lattice structure is so, structured. So the heat transfer, what is the heat transfer mechanism here for conduction? It is a lattice vibration only. So when the lattice vibrates from one body to the other body, the heat transfer will be very fast. But when you make this alloy, the lattice will not be in that form. Lattice will be compromised. Its structure will be compromised. That's why the huge changes in the lattice structure will be there. So what happens? Your heat transfer will not be happening at any of its pure metals. Okay, it is compromised a lot. That's why what happens is the thermal conductivity of an alloy will be lesser than the least thermal conductivity of its pure metals. My dear friends, this is a very important gate questions. Okay, most of the times this kind of questions are asked in the competitive examination, whether it is a gate or any given uh, competitive examination. This is the question that is given. Okay, let me give you one more question here. The thermal conductivity of nickel is 92 watt per meter Kelvin, and thermal conductivity of constantum is what? The constantum is made of 55% copper and 45% nickel. You must be knowing the copper thermal conductivity by now. It is 401 watt per meter Kelvin. In the previous question, we have seen this. Anyways, I will repeat the question here. The question goes like this: K of nickel is 92 watt per meter Kelvin. K of copper is 401 watt per meter Kelvin, and you made a alloy here that is called as constantum. And what is its thermal conductivity is the question. So you have an options here. Again, repeat kind of thing only. 401 watt per meter Kelvin, and the second option is 92 watt per meter Kelvin, and the third one is 401 plus 92 by 2 watt per meter Kelvin, that is the average, and the fourth one is 23 watt per meter Kelvin. So please tell me what is the right answer here.
23.
23.
23 is the right answer. All these are the wrong answer. So the right answer is 23. So it is as simple as that. So remember friends, here the point is the thermal conductivity of an alloy will be the lesser than the least thermal conductivity, lesser than the least thermal conductivity of its pure metals. Right. So that is the thing regarding the thermal conductivity here. So here what I should write, the thermal conductivity of pure metal will always be greater than the thermal conductivity of its any of its alloy. Whatever may be the alloy percentage doesn't matter. Pure metal will have highest thermal conductivity with, compared to the thermal conductivity of any of the alloys made out of it. Right. So this is one thing that I would like to tell you. So if I take thermal conductivity, so this is the next point of solids, and the thermal conductivity of liquids, and the thermal conductivity of gases. So among this, which one will have more thermal conductivity? Solid will have more thermal conductivity, or gas will have, or liquid will have more thermal conductivity? Please tell me.
Gases.
Gases will have more thermal conductivity. Yeah?
Solids. Solids.
Solids will have. So why solids or why gases? Can you give an example and explain?
Closed packet lattice structure in solids.
Very good. Closed packed lattice structure will be there in solids. This is very good answer. So here the lattice structure is closely packed. So the lattice vibration is very good here, and the heat transfer will be very fast by conduction here. The ability to conduct also will be very high. And when it comes to the liquids, if you take here, they are loosely packed. This is closely packed lattice structure, and this is loosely packed lattice structure. And when it comes to gases, what happens here? It is very loosely packed structure here. So what happens? The thermal conductivity of the solids will be greater than the thermal conductivity of liquids will be greater than the thermal conductivity of the gases. This is the order. Always solid will have highest thermal conductivity. You take any material in its given form, if it is a solid form. Let us take the example of water itself. Thermal conductivity of water. Water in solid form is called as what? Water in liquid form. Water in gaseous form. Agreed? Solid state, water is nothing but your ice. Ice will have very huge thermal conductivity when you compare it with the water. And when you go to the vapor, the thermal conductivity is very less. Okay, let me give this example. See, you touch the water. What is the chilling effect that you get? It's moderate. Okay, but when you touch ice, it's very high chilling effect. But when you touch water vapor, almost zero chilling effect. Okay, we always whatever the atmospheric air is there, it has water vapor in it. So you are touching it and you are not at all feeling that it is a chilled one. Okay, so that is the point here. So ice will have high chilling effect. Water will have moderate chilling, and vapor will have almost zero chilling, very less chilling effect. Okay, unless the temperature is very low, the water vapor will not have as much as the chilling that the ice will provide at the same atmospheric pressure, the same atmospheric temperature. So this is the thing with the solids, right? We'll move on to how the variation of the thermal conductivity will happen within the solids with respect to the temperature. And within the liquids and gases also we will see variation of K with respect to temperature. So in order to tell you this, I will draw a XY axis here. This is my X and Y axis. On my X axis, I will have temperature and I will have thermal conductivity on Y axis. This is how it is. So here I told you that the solids will have highest thermal conductivity. Okay, so I'll be drawing the solid lines on the top. This is the solids story, and then I will come to the liquid story. I told that liquids will have lesser thermal conductivity compared to the thermal conductivity of the solids. So I will come here, even lesser than the solids. This is the liquids, solids and liquids, and then I'll have gases also. So this is how the temperature variation happens in solids, liquids, and gases. Okay, you can observe the thermal conductivity solid is high, then liquids, then gases. So that is also observed very clearly in this graph. Okay, so what do we want here is what happens to the thermal conductivity if the temperature is varying. Let us look at the case of solids first. In solids, if the temperature is increasing, Okay, what is happening to the thermal conductivity? It is increasing or decreasing? Look at the graph and tell me.
Decreasing.
It is decreasing.
Decreasing, sir.
Yeah, good. In liquids, if the temperature is increasing, what happens to the thermal conductivity? It is increasing or decreasing?
Decreasing.
Decrease.
It is
Decrease.
decreasing. In gases, what is happening to the thermal conductivity if the temperature is increasing?
Increasing.
Increasing.
It is increasing. Okay, so you can look at the solids. What happens? I am increasing the temperature. When I am increasing the temperature, the solid K value is coming down. So if the increase is there, the thermal conductivity should be decreasing. Then what happens to the liquids? Liquids also same trend as that of solids. If the temperature increases, the thermal conductivity is reducing. Okay, let's show with these colors only. Here it is reducing, here it is reducing, and here it is increasing. As you go on here, the thermal conductivity is increasing here. So you remember this graph. When you remember this graph, you should be able to tell whether what happens to thermal conductivity is here. You'll be able to tell. So why is this happening? Okay, the temperature is increasing, the thermal conductivity is decreasing in solids and liquids. Why? And in gases, reverse trend. Why? What is the reason?
Sir, in gases, as it is loosely packed, when we increase the temperature, the molecules have space to vibrate. But in solids, as they are already closely packed, even when we give heat, there is no chance for getting vibration and to transmit heat.
Good, very good. See, the point here is in solids and liquids, we have already seen that they are a bit closely packed there. Okay, since they are closely packed, what happens is they will try to move away from each other when the temperature is increasing. So when they move away from each other, what happens is the heat transfer will decrease. The rate of heat transfer will decrease here. That is the reason why the thermal conductivity will decrease with respect to the temperature. If the temperature is increasing, thermal conductivity will decrease. But whereas if it go to gases, what happens is your molecules will try to come near to each other. Okay, as the temperature is increasing, the given molecule will vibrate at a higher rate. That's why the thermal conductivity will increase. That is due to its physical mechanism that is available in each state here, in solids and liquids and gases. This behavior is expected in all of them, right? So but this is in general, but there are few exceptions which you must note. Okay, there are few exceptions in solids, especially uranium. If you take uranium is also a solid. In general, if the temperature increases, what should happen to thermal conductivity? It should decrease. That's what should happen. But in case of uranium, the thermal conductivity will increase. Okay, why is it happening? Again, due to the same story, because of the lattice structure. The lattice structure will get even robust when you increase the temperature for uranium. Uranium is a solid, but it behaves differently compared to the other solids. And also you have one more material, that is aluminium. Okay, in aluminium you will have various temperature variations actually. Okay, if the temperature of aluminium is less than minus 135 degrees centigrade, then if the temperature increases, thermal conductivity will increase. And if it is minus 135 degrees centigrade to 390 degrees centigrade, then if you increase the temperature, thermal conductivity is going to be constant and it is not going to vary. And if the temperature of Aluminum is greater than 390 degrees centigrade. If the temperature increases, the thermal conductivity will decrease. Okay, so this nature of thermal conductivity decrease with the increase in temperature will be available in aluminum only after 390 degrees. Only above 390 degrees this is observed, but below 390 degrees there is a different thermal conductivity variation which you should remember, which is minus 135 degrees. Below it is thermal conductivity increase, and between minus 135 to 390 the thermal conductivity is constant. I hope it's clear.
Yes, sir.
Yeah. Why is this happening? Because of its microstructure, or you can say the lattice structure also. This is the reason. Right. I should have told you one more exception here. I generally told that thermal conductivity of the diamond is highest, but I forgot to tell you the exception here. The exception for the highest thermal conductivity is if the temperature is greater than 100 Kelvin, then diamond is the highest. If the temperature is less than 100 Kelvin, then copper is highest. Okay, so in general at room temperature diamond is highest, but if you have very less temperature, less than 100 Kelvin means what? Minus 173 degrees centigrade. So it's very less temperature. At that temperature, diamond will not have thermal conductivity as much as copper. It will have very less. Copper will have around 400 watt per meter Kelvin. We have seen. Okay, less at lesser temperatures, the thermal conductivity of the diamond is even lesser than the copper. That's why this exception also you should have in mind. Right. So we are discussing about the thermal conductivity variation with respect to the temperature. So I hope I told everything in this one. We'll move to the next topic here. Next point regarding thermal conductivity. Next point is, if I should say generally the thermal conductivity is high K, that will represent high electrical conductivity also. This is the most general thing. See, we told that the copper is having highest thermal conductivity. Okay, and this copper will also have high electrical conductivity. That is the reason why it is used in the wires. The electrical wires you see, they are made of copper. Why they are made of copper? Because copper has very good thermal conductivity. It has very good ability to transfer the heat, and also it has very good electrical conductivity, most importantly. So it has electrical conductivity. That is the reason why you are using it as a wire for transferring the electrons or the current from one place to the other place. Okay, so most of the cases, if the K is high, the electrical conductivity will also be high, but a diamond is an exception here. Okay, here the exception is diamond. Diamond is excellent thermal conductor and very poor electrical conductor. So it has very good thermal conductivity and very poor electrical conductivity. This should be kept in mind. But most of the materials, if the thermal conductivity is high, electrical conductivity is also high. Example is copper, aluminum, so many things you can take, right?